covers a wide range of topics in the space of CCUS, hydrogen, and EOR. That contains CO2 capture, including direct air capture, CO2 conversion by electrochemical processes, CO2 storage, CO2 mineralization, hydrogen carrier, and EOR, IOR in shale and heavy oil. And some of the results are presented in the poster session. So Omar and Teslim are part of the audience today. So Omar has two posters. One is on electrochemical conversion of bicarbonate into formate. And we are converting bicarbonate instead of CO2 because it's more energetically efficient, and the bicarbonate can be generated upon CO2 capture by tertiary amine. So we are integrating CO2 capture and conversion that way. So he has one poster on that, and another poster he had is on CO2 capture by organic carbonates. So it's also a new CO2 sorbent that works in the water phase. That's a very interesting poster. And Teslim is showing details of nanobubble experiment and modeling. He is currently working on also EOR application of nanobubble. Okay, so for CO2 sequestration part of the consortium, we study different types of carbon carriers for in situ and ex situ carbon sequestration processes. So CO2, when it's used as a carbon carrier, as a pure fluid at the supercritical state in subsurface temperature pressure, the carbon density is 15 to 20 mole per liter. And it has some shortcomings, including geological sequestration, where buoyant forces are going to cause the CO2 plume going upward with low pH, and also compression cost of handling gas CO2 is also an issue. And then last year, I presented a new idea of using a formate as a carbon carrier in the water, so we don't have to spend a lot of money for compression of gaseous CO2. But today, I'm going to focus on nanobubble of CO2 as a way to also contain CO2 in the water phase. And we also study some different types of carbon carriers. And one of them is what I mentioned just a few minutes ago, organic carbonate. That's a very interesting CO2 sorbent in the water. And also, there are some synergistic mechanism of using a different kind of carbon species. For example, we can control CO2 plume by using a formate as a buffer solution in the water phase. And also, the synergy can be utilized for CO2 mineralization. So for that, we are studying in situ and ex situ mineral carbonation using different mechanisms. So now I'm going to focus on nanobubble. So aqueous nanobubble dispersion of CO2 for geological carbon sequestration. So nanobubble is a very interesting but very complicated the fluids. And we don't know still many things about it. So I'm going to present some initial results we accumulated over maybe past 2 years, but of course you can throw stones at me at the end of the presentation. So first I'm going to start by showing an interesting result using a CO2 nanobubble, and then present some modeling framework. And we want to model it because it's very difficult to measure all kinds of properties for high pressure nanobubble. For example, nanobubble size at the high pressure. So it's very hard to measure at the moment. But if we have a thermodynamic model, and we can calibrate it with some limited data, and the model is going to predict all kinds of equilibrium properties. So that's the idea. And then result part is focused on nitrogen because CO2 is more complicated in the water. So at the moment, the model doesn't model the electrolytes very well. So that's limited for nitrogen. So there's a transition from CO2 to nitrogen. So I'm telling this in order to avoid a confusion. So applications of nanobubble technologies include EOR and CCS. So we started the nanobubble research by contract project on tight sandstone half-and-puff using CO2. And in one case is a supercritical CO2 half-and-puff, and the other case was CO2 nanobubble half-and-puff. And results shown here indicates that oil recovery was systematically greater with using a nanobubble in comparison to supercritical CO2. And the results are very interesting and promising, but unfortunately we got more questions than answers. So we went back to fundamental measurements of nanobubble properties. So that led to this presentation. And another application is geological carbon sequestration. So as you know, carbon fix in Iceland use carbonated water for mineralization in basaltic formation. So hypothesis here is maybe we can enhance the carbon content and also kinetics or reactivity of this injection fluid and minerals using a nanobubble of CO2. So here I'm showing a snapshot of a nanobubble sample at the high pressure, 3000 psi, and the sapphire cell. This has an internal volume of 15 cc. And you see it looks like a clear water, but this contains good amount of CO2 gas. So after isothermal expansion or constant mass expansion, you see visible bubbles there. And volume after expansion is as much as 360 cc. So this corresponds to 2.3 mole of CO2 per liter of DI water. That's 1.5 times the inherent solubility of CO2 in DI water. And depressurized sample was analyzed using nano tracking analysis. So deep pressure sample in open system was analyzed using this tracking analysis. And you see videos for days 1, 2, 7, and 10. And table below shows measured diameters for different days and number densities. So you see bubbles are very energetic for the first 2 days, and much less on day 7 and day 10. And the diameter is decreasing over time from 2 digits to 3 digits in nanometer. And number density for days 7 and 10 are order of 10 to the power of 8. And days 1 and 2, we couldn't measure it because that was too high, too many to measure using this analysis. But clearly, it should have been much greater than 10 to the power of 8 per cc. And again, this is for low pressure open system. So you see it's kinetically stable. And this kinetic stability of nanobubble was the reason for the wide application for low pressure systems such as agriculture and wastewater treatment. But at the moment, there's no systematic understanding of properties, and therefore, application of nanobubble for high pressure systems, including our surface application, has not been established. So that is the fundamental motivation for our study. So we started by measuring gas content because that's very fundamental data. So y-axis is the CO2 content in mole per liter, and the horizontal axis is pressure of the system. And the red curve is the inherent solubility of CO2 in DI water. And measured data are black dots. So you see 1.5 times greater gas content was observed with nanobubble in comparison to inherent solubility of CO2 in the water. And then we changed the water properties. So the two bar charts on the left is the original data from previous slide, and brine case is on the right side. So you see, because of salinity, inherent solubility of CO2 decreases from 1.5 to 1.9 mole per liter, but the nanobubble can enhance the gas content from that point. And again, the enhancement factor is 1.5. And we also changed the brine case using a buffer solution based upon sodium formate. And sodium formate can suppress the pH change upon CO2 dissolution. So that's how the buffer solution can enhance solubility of CO2. So you see on the left-hand side, the inherent solubility of CO2 was enhanced from 0.9 to 1.1 mole per liter, only by just a buffer solution. And then nanobubble enhanced that by the factor of 1.5. So for some reasons, the enhancement factor is always 1.5. And so that indicates that maybe we can enhance gas content in nanobubble by enhancing this red bar, which is the inherent solubility of CO2 in the solution. So using that idea, we recently was able to enhance the gas content, CO2 gas content in nanobubble to 3 mole per liter. That's very new data we got a few weeks ago, and we did it by increasing the inherent solubility of CO2 in the water by adding organic carbonate sorbent in the water, just as an additive. So that's a new data. It's not shown here. So now let me talk about some thermodynamic aspect of nanobubble dispersion. So a system at a fixed temperature, total volume, and the total mole numbers of the components is at the equilibrium when Helmholtz free energy of the system cannot be reduced by perturbation of state variables. So this dA total is a change in Helmholtz free energy for the total system, and this is going to be 0 at the equilibrium of the system when Gibbs free energy is minimized. And at the equilibrium, net mass transfer between bubble and the external water phase is 0. So chemical potential for all components are equal for the two phases, bubble and external water phase. So this gives a second term on the right-hand side, 0. So therefore, we have a constraint at the equilibrium. So that is capillary pressure, pressure of bubble, less pressure of water, being equal to the product of interfacial tension and derivative of total surface area with respect to the volume of the vapor phase, which is a well-known Young-Laplace equation in the case of spherical bubble, as in our case. So key point here is that we need a NC plus 3 variables to be set for equilibrium system of nanobubble. So this is one additional variable in comparison to conventional two-phase system with a planar interface. And the reason for one additional variable needed here is because we allow for different phases have different pressures. And for this NC plus 3 variables, we set the temperature, total volume, external pressure, and the mole number of the components. And another important point in modeling is that the external water phase is supersaturated by gaseous species. So to illustrate the problem, I'm showing here Gibbs free energy for binary system of water and nitrogen. So the solid curve on the bottom is Gibbs free energy for the binary system at the pressure of 70 bar. And the equilibrium phases, water phase and gas phase, are connected by this common tangent line. And the water phase on the left is pure, almost a pure water with a very small amount of nitrogen solubility. But when we have a capillary pressure, so gas phase has a higher pressure. So in this hypothetical case, it's a very high pressure for the gas phase. And this is for exaggeration on purpose, right? So the gas phase Gibbs free energy is shown by dashed curve above. Now equilibrium phases are connected by common tangent line from solid to dashed curve. Now equilibrium liquid phase now is shifted by this red line, and this is the supersaturation of water phase by nitrogen in this case. So key point here is that now equilibrium liquid phase is sitting on the metastable zone in the Gibbs free energy surface. So this is not easy to model using a simple equation of state. So we used the advanced equation of state to make sure that metastable zone of energy is reliable. And our case, we use the GERG-EOS, G-E-R-G equation of state. Now, experimental setup are systematically shown here. So we have 2 pumps and for water and nitrogen, and they are co-injected into core holder that contains a porous membrane filter for nanobubble generation. And the resulting bubble, nanobubble, is received in the receiving accumulator with piston. And the figure on the left top is a porous membrane filter we used. This has a pore diameter of 5 micron, but resulting bubbles are nano size. And the core holder is here, and this contains these membrane filters inside. And the figure on the right is a sapphire cell we used. Now, I mentioned that we need to specify NC plus 3 variables that are temperature, external pressure that we can measure using this pressure gauge on the left. And then total volume of sapphire cell is known, 15 cc. And the more numbers of components are not directly measured, but we back calculate by constant mass expansion and material balance along with the equation of state. So that's how we set NC plus 3 variables. And here's a deep pressurization snapshot. So initially clear water, but after deep pressurization, you see visible bubbles. And the small gas cap on the right is connected to external accumulator. So here's a result of nitrogen nanobubble gas content. So the DI water and the brine case both are similar to each other, and enhancement factor is 3 with respect to the solubility of nitrogen in DI water. So those data are matched by the equation of state, and once the equation of state is calibrated, that gives all kinds of equilibrium properties such as capillary pressure, radius of bubbles, surface area, number density, saturation of phases, and interfacial tension. So that's a benefit of using a thermodynamic model. That gives predictions for the parameters that are not directly measurable. So you see the capillary pressure increases with external pressure, and radius of bubbles goes to even close to single digit for high pressure sample in nanometer. And surface area is as much as 1 square meter per cc of nanobubble sample for high pressure sample. So this large surface area is going to allow for rapid mass transfer as needed from gas to water. And the number density goes even beyond the 10 to the power of 15 for high pressure sample. But we need, of course, validation by using a direct measurement. And here I'm showing supersaturation water phase by nanobubble. Supersaturation by gas phase, gas species in the external water phase. So dashed line is the measured data, and dotted line is thermodynamic the solubility of nitrogen in the water. So you see this gap, that's supersaturation. And the interesting thing is that actually the supersaturation is the main reason for enhancement of gas content in nanobubble sample instead of nanobubbles by themselves. So here I'm showing the fraction of nitrogen as a bubbles as a function of pressure. So you see it's only 10 to 20% of nitrogen is actually in the bubble form. So when we say nanobubble, bubble sounds important, but actually major contribution for the gas content is actually molecularly dissolved form of nitrogen. And bubbles are important because that can enable supersaturation water phase by gas. And we can model IFT as a function of phase compositions because the equation of state is quite reasonable. So here's a conclusion. So it's possible to solve for thermodynamic properties of aqueous nanobubble fluids. So we plan to calibrate the model for high pressure data by using dynamic light scattering that we are working with a company to make a prototype for our purposes. And key point is that nanobubble, the bubble by themselves are not the main gas storage. Instead, the presence of bubble allow for supersaturation of the water phase by the gas. So that's the main contribution of gas content. And we are studying use of nanobubble for EOR, CCS, and also enhancement of mineral dissolution and precipitation in mineralization process. With that, I'd like to thank consortium members of the Energy Simulation Industrial Affiliate Program on Carbon Utilization and Storage at the UT Austin. So I would be happy to answer any questions.
Thank you, Ryosuke. Any questions, comments? Okay, Dr. Okuno, I'm pretty pleased actually. From May, our visit, we're talking about your nanobubble technology and other methods. The fact that you're able to come up with an equation of state to actually, go forward to make better predictions, and actually handling salinity and pH. Just one more thing, the slide number 11, you don't have to pull that up. You basically have an equilibrium situation with a fixed temperature. So with the next thing, you'll be looking at, injecting, say, a CO2 carbon, different temperature going to a formation. So would it be some temperature effect affecting the bubble stability?
Yeah, definitely. Temperature is, I think, a major factor that affect properties, including stability too. So, yeah,
that was part of the exercise you'll be looking.
Yeah, we will do. And Tesla is working day and night.
Okay, that's easy to pass the buck, right? Okay, thank you, Paul.
From your previous MSc student.
Yeah,
So
that's right.
So I was wondering, how would the nanobubble works in porous media? Would that have interactions with the rocks?
Yeah, so I think the what is directly in contact with the rock surface is actually molecularly dissolved CO2 in the water, and nanobubble are supposed to give this dissolved CO2 as needed when water phase can accommodate more CO2. So yeah, I think again important CO2 is actually in the water phase, not in the bubble phase.
And one more question is it difficult to really scale up to creation of those nanobubbles?
So we found that the higher pressure is easier to make a nanobubble. So obviously it's easier if we can do it subsurface as part of the downhole tool. And of course, for that case, we cannot use a porous membrane filter because of potential plugging issue. So, but there are many other ways to make a nanobubble using a hydrodynamic mixing method.
So
is also working on that.
So essentially, it would be easier to create nanobubbles in higher pressure.
Yes, that's
higher
right.
temperature.
That's right. But even when you make at suboptimum conditions, the nanobubble is actually kinetically very stable. So it's not much of an issue. Maybe, but we have to test it. Yeah, we have to test it.
Thank you.
Eric?
Thanks. That's a really nice presentation. It's nice to see these techniques to try and improve storage of CO2. Can I ask about the viscosity? Well, a couple of questions related to the viscosity of the aqueous solution and injectivity. How you would achieve that? Are you, the mixing would be downhole at pressure, and would you be extracting water from the formation in order to achieve that, to avoid over-injecting fluid into the... Does that make sense?
So one company planning to do a field pilot in 2026 is planning to use waste, the produced water, and they have CO2 from produced natural gas, and then make a nanobubble from that.
Okay.
And we measure the nanobubble apparent viscosity using Berea sandstone of maybe 80 nanodarcy or something. And viscosity was increased by 10% with respect to solid brine. That was also done by Tesla, by the way.
Yeah. Okay. Thank you.
Okay, a couple of questions online from William Rawson. How are the bubbles created in your apparatus? First question. And normally bubbles created in flow through a porous medium by snap-off are roughly the size of the pore throats. But in your case, bubbles are 1,000 times smaller. So how are the bubbles created in your apparatus?
Okay, so I think the question is maybe the difference between the pore size in membrane filter and the actual size of bubbles generated. So,
I guess.
okay. So bubble size is determined by I think many factors, mainly thermodynamic factors, and the bubble size are strongly affected by pH, meaning ionic species, temperature, and of course the gas species, like nitrogen and CO2 are very different. And we tested using a smaller pore membrane filter. Instead of 5 micron, we used a 2 micron, but we didn't see much difference in the resulting bubble size.
Okay.
Yeah.
Another one is from William Rawson as well. Coarsening of forms of much larger bubbles by diffusion between bubbles is much faster in CO2 form than nitrogen form because of the greater concentration and therefore faster diffusion through liquid than nitrogen. Do you think that might affect your results?
I think I need to talk to Dr. Ross.
Okay. You know him well, good.
Yeah.
Okay.
Yeah.
Question, mechanically, when you inject a nano bubble through the pipe and through porous media, would a shearing force affecting the stability of the bubbles?
Yeah, I think we have to test it. Yeah.
Okay,
Not yet.
not
done.
yet.
Yeah.
Okay. Once again, thank you, Dr. Okuno, for your
Thank you.
presentation.